The electricity in your room just traveled hundreds of kilometers to reach you. Here's how. And no, that is not an exaggeration. We flick a switch, the lights pop on, and it all feels so instant. But the energy that's powering your screen right now has been on a truly epic journey. So come on, let's follow a single packet of that energy, from the very moment it was born to the instant it arrived right there with you. Every journey's got a starting point, and for our electricity, that's almost always a power plant. This is the birthplace, where raw energy gets converted into the electrical current we can actually use. Now, here's the really cool part. This basic idea works for so many different power sources. It doesn't matter if it's steam from a thermal plant, the force of the wind, or rushing water. The goal is always the same: spin a turbine. That spinning motion turns a gigantic magnet inside a huge coil of copper wire. And that's what gets the electrons moving. And that flow of electrons, well, that is electricity. Okay, to really get the rest of this journey, we need to talk about two key things: voltage and current. And honestly, the easiest way to think about them is with this simple water analogy. Think of voltage as the pressure that's pushing the electricity, like water pressure in a hose. And current, that's the actual flow or volume of electricity moving through the wire. Keep that in your back pocket because it's about to become super important. So, our electricity is born, but it's got a long, long way to go. And traveling hundreds of kilometers through wires is not easy. It needs to be prepared for the trip, and that means giving it a massive, massive boost. You heard that right, 500,000 volts. Going back to our water analogy, this is like taking that electricity and putting it under an absolutely insane amount of pressure. This is the kind of voltage that's zipping through those giant metal transmission towers you see stretching across the countryside. I mean, it seems crazy dangerous, right? And it is. So why on earth do we crank the voltage up to these extreme levels just to send it on a long-distance trip? Well, the answer is all about efficiency. See, when electricity moves through a wire, it faces a kind of friction which generates heat. It's called joule heating, and it means energy gets wasted along the way. But here's the clever trick. By jacking up the voltage, the pressure, you can deliver the exact same amount of power with a much smaller current, or flow. And less flow means less friction, which means way, way less energy is lost as heat. So those super high voltages are what let electricity travel all the way across the country without just fizzling out. All right, our electricity has made it across the country and it's finally arrived in your local area. But at 500,000 volts, it is still way too powerful, way too dangerous to enter any building. So it's time to bring it back down to earth. Now, this step down doesn't happen all at once. First, those high voltage lines enter a regional substation. You've probably seen them. They're those big fenced-in yards full of wires and equipment. That brings the voltage way down to around 7,000 volts. Then, for the very last step, a local transformer, you know, that gray can on a utility pole, or maybe a green box on the sidewalk, brings it down to a safe, usable level for your home. The journey is almost over. The electricity is now at the perfect voltage, just a few meters away from your wall outlet. These last few feet are handled by some really crucial hardware. That service drop is the wire that makes the final leap from the main line to your house. It connects to your electrical meter, which, of course, is what tracks how much you're using. From there, it goes into your breaker panel. Think of that as the final gateway, the control center that safely directs the power to all the different circuits in your home and protects everything from surges. So the electricity has finally arrived. But here's a twist. Depending on where you are in the world, that final voltage that comes out of your wall isn't exactly the same. Turns out there isn't really one single global standard. The world is pretty much split into two camps. You've got North America and Japan, which are in the 100 to 127 volt bucket. This standard was adopted really early on, partly because of safety concerns with insulation technology way back in the day. Then you have most of the rest of the world. Europe, Asia, Africa, they use 220 to 240 volts. And it's a fantastic example of a trade-off. The higher voltage is more efficient and lets you use thinner wiring, but the lower voltage was at the time seen as being a bit safer. And as you can see right here, that higher 220 to 240 volt standard is actually way more common around the globe. And here's a fun piece of tech trivia for you. It's not just the voltage that's different, but the frequency too. North America uses 60 hertz, while much of the world is on 50 hertz. That little difference is exactly why an electric clock from Europe would actually run at the wrong speed if you plugged it in the United States. So when you really stop and think about it, the whole journey is just incredible. It starts as pure motion in a power plant, gets transformed into this ultra-high pressure energy for a cross-country sprint, and then it's carefully stepped down, level by level, until it's finally gentle enough to power your life. This system of generation and distribution was truly one of the greatest engineering marvels of the last century, no question. But as we move towards things like renewable energy and much smarter technology, you have to wonder, what will this amazing journey look like in the future? What's going to change, and what parts will stay the same? That's something worth thinking about.